are the PhD students that participated in the CERN summer school in Romania. Am I right? Yeah. Yes. So in case you don't know, I'm the Romanian Minister of Education, Research, Youth and Sports. I'm particularly happy that we were able, thanks to the CERN organization, to welcome you in Romania. And I just want to hear by a single word if everything was okay or not. I'm extremely honored and happy that Dr. Rolf Heuer is giving us a conference today. Needless to say that Dr. Heuer is the Director General of CERN. I'm saying this more for the Romanian press and for those that are not in the field. The title of the conference is the Large Hadron Collider LHC, Shedding Light on the Early Universe.
So particle physics and accelerators, what is our job? We explore the innermost structure of matter, and we ask two main questions. Which are the fundamental constituents of matter? And which forces interact between them? These are the two big fundamental questions we are asking. And when we investigate the structure of matter, when we try to answer, so when we ask these questions, when we try to answer these questions, and we are in that way investigating the structure of matter, we also gain understanding of the early universe. How do we do this? Well, the role of accelerators is easy. You resolve the inner structure of matter. I mean, it's obvious. If you have an object which you want to investigate, your probe with which you investigate it must be smaller than the object. Otherwise, you cannot resolve the object. That's quite obvious. You use a magnifying glass, a microscope, etc., etc. You go bigger and bigger. And the key word is energy. And don't worry, I have only 3 formulas in my whole talk. Okay? The first 2 are here. The higher the energy, the smaller the wavelength, that means the smaller the probe, so you can investigate the small structures. High energy also has a big advantage because due to Einstein, E equals mc squared. Higher energy means you can produce particles with higher mass. Yeah? So you can investigate new particles, which you normally don't have. And with accelerators, you have high statistics and a lot of data, you can do precision experiments. So, what needs acceleration? Well, take a positively charged particle like the nucleus of the hydrogen atom, the proton, and you take a battery with 1 volt, the proton has charge 1, this is this 1E, it runs over the voltage of 1 volt, and then it gains an energy of 1 electron volt. At the LHC we have 2 times 7 TeV. Now 1 TeV is 1 million times 1 million eVolt. So if you would do it with batteries, you would need 2 times 7,000 billion batteries. That means 14 batteries per star in the Andromeda galaxy. That would be a little bit stupid, so we do it differently. But what do we do with these accelerators? Now this is, unfortunately I cannot move. This shows you the evolution of the universe on one transparency. On the left-hand side you have the Big Bang. On the right-hand side we are today, roughly 13, 14 billion years after the Big Bang. If you go 1 billion years after the Big Bang, the stars and the galaxies have formed. And if you go 300,000 years after the Big Bang, atoms have formed. Why did they only form 300,000 years after the Big Bang? Because at the Big Bang it was a tremendous amount of energy, very hot, very tiny universe, which then expanded. Now when it expands, it keeps its energy, but the temperature goes down. So it cools down. And at 300,000 years after the Big Bang, the universe was cold enough so that stable atoms could form. And when you look today into the universe with telescopes, you only get information after 300,000 years after the Big Bang. So you don't get any information below 300,000 years. with our accelerators, we come much, much closer to the Big Bang. We come as close as 10 to the minus 12 seconds. Now what does this mean, 10 to the minus 12 seconds? It's a millionth of a second. Pretty close. In human terms, it's very close. In terms of the development of the early universe, it is still very far from the Big Bang because a lot has happened in this short time. But one prediction I make is that particle physics at the energy frontier with the highest collision energies ever produced by mankind will most probably in the next few years change our view of the universe. And this is the fascination of doing this physics. This is on a different scale here. This is from the Big Bang, essentially point-like, 10 to the minus 32 centimeters, up to the universe today, 10 to the 28 centimeters. This is the development of the universe. It's today 10 to the 28 centimeters. Don't ask me what 10 to the 28 means. It's a large number. But if you replace the centimeter by dollars, you have roughly the square of the American deficit. I still cannot imagine that number. Okay, it's a large number. Okay, but the US is a large number. Okay, it's a large number. So I think it's difficult to imagine the small, and it's difficult to imagine the large scales. What is easy to imagine is our human scales. And I have selected here Mr. Rutherford, because Rutherford, 100 years ago, investigated the structure of matter. It was the start, to some extent, it was the beginning of the nuclear physics, because he found out that, surprisingly, matter-wise, we are essentially empty. Yeah? I mean, because the atoms are essentially empty. They have the nucleus in the atom, and then you have the electron clouds around it. But it's essentially empty concerning matter. Yeah? It's all forces. So that was the start of nuclear physics. Now, at the large scales, we are looking into the universe, into the history of the universe with space-based telescopes like Hubble or AMS and ground-based telescopes, ALMA or the Very Large Telescope. And they give the picture of the history of the universe up to 300,000 years after the Big Bang. Now, what we are doing, we are going to the small scales, 10 to the minus 16 centimeters. 3 orders, 1,000 times smaller than the proton, than the nucleus of the hydrogen atom, because the Large Hadron Collider is nothing else than a super microscope. These accelerators are super microscopes. Yeah? With high energy, they look into the small particles, but you see, you come pretty close to the Big Bang here. It's still a lot of orders of magnitude away, but we are coming as close as nobody else. So what we have learned in the 100 years from Rutherford to today is the atoms that's in the center here consist out of the nuclei and the electron. And then the nuclei consist out of protons and neutrons, and these protons in turn then consist out of quarks and gluons. And these are the smallest today to us known particles and constituents of matter. And when we study the physics laws of the first moments after the Big Bang, we have a fantastic symbiosis between particle physics at the small scale, astroparticle physics, astronomy and cosmology on the large scale. So this is a fantastic symbiosis. Now let's see what we have learned about the small scale, the quarks, etc., etc. Okay, matter particles. Matter particles are quarks and leptons. Leptons is, for example, the electron and the electron neutrino. The electron and the electron neutrino. And the nuclei consists out of up and down quarks. And the mass relation is shown here. The smallest mass is the electron neutrino. This is where the arrow points to, and the other things are a bit heavier. Actually, that's all we need. That's in principle all we need, because all of you consist only out of these particles. You are very different, but you all consist out of an up quark, of up quarks, of down quarks, and of electrons. That's all. Okay, I left some space on this transparency because nature has decided nature needs more. So, nature has introduced the same family again, 2 quarks and 2 of these leptons. And they behave exactly the same as the first family. The only difference is these particles are more massive. Much more massive. And then nature decided, okay, 2 are not enough, we need 3 families. And that's the third family again, 2 quarks and 2 leptons. A huge difference in mass. A huge difference. This top quark, which is in the top right corner, is as massive as a gold atom. It is as massive as a gold atom, nonetheless it's a point-like elementary particle. Okay, and that's it. That's the microcosm. 3 families consisting out of 2 quarks each, 2 leptons each. So this is, so to speak, the Mendeleev table of chemistry in the microcosm. Just 12 entries. Very easy. So, matter consists of 3 families of quark and leptons. Matter around us, that means we need only one of the 3 families. Now, matter at high energies is, so to speak, democratic. All 3 families are present. So if we go to high energy and study the matter at high energies, we get knowledge about the early universe because it was democratic. So, that's the connection between matter and the early universe. What about the forces? Now we know 4 forces in the microcosm of the early universe. Gravitation, which acts on mass and energy. Electromagnetic forces, which acts on electric charges, so keeps the atom together. The weak force acts on all the particles, the leptons and the quarks. It's, for example, responsible for the processes in the sun. And the strong force, which acts only on the quarks, but which binds these quarks together. And we need all these 4 forces. And these forces are exchanged between the matter particles through force carriers, which we call gauge bosons. So each force has its own carrier or its own carriers. The graviton for the gravitation, the photon for the electromagnetic, the W and Z boson for the weak force, and the gluons for the strong force. So, 4 fundamental forces act between matter particles through this exchange of these force particles. In our regime, the respective strengths of the forces is very, very different. It goes up to 40 orders of magnitude, so that's a 0 with 40 zeros behind it. It's a huge difference between the forces in our energy regime. At high energies, and we have indications of this, at high energies the forces seem to become of the same strength. So the question is, was there a single force at the very beginning? So if we study the forces at high energies, we see if the forces can get united at high energies, and we get knowledge about the early universe. So this is what we have learned over the past 40 or 50 years. And I call it the discovery of the standard model of particle physics. The physical world is composed out of quarks and leptons. These are these 3 families. You see the 1, 2, 3 with 2 quarks, 2 leptons each, which interact between themselves via these force carriers, and the force carriers are these blue things on the right-hand side, the photon, the gluons, and the W and Z. This is all what we need to describe the microcosm and the early universe. At least that's the static picture. Now, of course, you have to introduce the dynamics between these particles. You have to describe the dynamics, and the dynamics you only can describe as mathematics. And the mathematics is a standard model of particle physics. It's a mathematical formalism which describes all interactions which are mediated through the weak, the electromagnetic, and the strong forces. We have tested this model over the past 40 years to very high precision, down up to energies of 100 GeV, so roughly a factor 10 to 100 less than what we do now, and down to 10 to the minus 18 meters. And this standard model is fantastic. It's really fantastic. It withstood essentially all these tests, which is a fantastic achievement. It's fantastic. It's absolutely frustrating on the other hand, because there is one piece missing within the standard model.